So the next topic, which is the method of transformation, which we have seen before a few times in, say, the lecture note for chapter 3 and 4, but we will revisit this. So this is the topic of section 6.4 in your textbook. So we have seen this monotone transformation result that was used liberally in earlier lectures. In fact, it is question 7 in your midterm 2. So it should be familiar to you by now. If you have a continuous random variable with PDF f, and you have a function g that is either monotone increasing or monotone decreasing, then y, which is a transformation of x, has PDF given by this form here. Well, you have to pay attention to the absolute value of the denominator. So we have seen this example several times. So this here is in the case of a single random variable, and you transformed it by another function g, univariate. So the function g is univariate. But let us twist this around. An interesting twist. You can apply this to the case of bivariate random variable by introducing what is known as an auxiliary variable. But let's see how the implication goes. Suppose I have a bivariate continuous random variable. It has chosen PDF f here. And now I let a random variable z, which is some function of x1 and x2. And the key point here is, and I think maybe this is, so this should be g is equal to g, not s. So the key point I want to say here is that such that for all arbitrary but fixed value of little x1, the function h now, which is really the function g, but with x1 fixed, and it's just a function of x2, we require this function is either increasing in x2. So conditional on the value of x1 equal to little x1. Chapter 5 of your textbook talk about the conditional CDF, which, as we refresh your memory, is, I would say, well defined, except that one cannot really condition on the fact that x2 is equal to x2 because that's a set of property 0, but you understand what we mean. So in any case, the conditional CDF of z, given that x1 equal to little x1, you can write this as this form. So the random variable x2 fixed at x1 equal to little x1 is just equal to z. And because this function, we can replace it with h, because hx2 is just gx1. hx2 let's say equal to z. And now because h is increasing, I could take it inverse. So that's the inverse is just x2, the random variable, let's say h inverse z. And so this is nothing more than the cumulative CDF evaluated h inverse of z. So what that implies is that I could then say the conditional PDF is just the derivative, conditional PDF is just the derivative of the conditional CDF. So the derivative with respect to z of the conditional CDF. And so by the monotone transformation theorem, this is once again the monotone transformation. We have the conditional PDF of x2 given x1 divided by the transformation inverse. So that's the monotone transformation we saw earlier. So doing why does we do this operation? Well, so the joint PDF the joint PDF of z and of x1 is then given by the conditional PDF of z multiplied by the marginal PDF of x1. So the conditional PDF of z multiplied by the marginal PDF of x1. And this, as you can see, is nothing more than now the joint PDF of x1 and H inverse of z. We recall that H inverse of z is such that H x1 or G x1 x2 is equal to z. So this is a perfectly well-defined value for x2. So if that's the case, I have the joint PDF of z and x1. Then to get the marginal PDF of z, I just have to integrate it with respect to the random variable x1. So the marginal PDF of z is integration of the joint PDF with respect to x1. And so I have this expression here as the marginal PDF of z. And so you can see this looks very much like a monotone transformation result. So that's the beauty. By applying the monotone transformation carefully, you can get the marginal PDF of some function z by looking at the joint PDF of x1 and H inverse z, because as you will remember, H inverse z is basically the inverse with respect to a fixed value of x1 for x2 equal to the value z. And the case when g x1 x2 is decreasing can be derived similarly. That's why we put the absolute value here. So this is just a derivation. You may go back and check the notes again just to convince yourself that this derivation is kosher. But the main reason why this derivation is so useful is that it gives us a few very interesting examples. So let's go back. Suppose the function g is now the sum, x1 plus x2. Then for a fixed value of x1, the inverse average at z is just z minus x1, because x1 plus x2 is equal to z. And so the transformation by the monotone transformation, the Jacobian in that case is simply 1 here. So we have replaced the formula. We go back. This here, x1, H inverse of z. So that is simply x1 and z minus x1. And this quantity is 1, so there is no denominator. And that is nothing more than a convolution formula for x1 plus x2. But another more beautiful use, and this is problem 6.67 in your textbook, is suppose you have a product of two random variables. Then for a fixed x1, x2, which is z divided by x1, a very simple transformation. And so the Jacobian in this case is the absolute value of x1. And so you have this formula for the PDF of x1 times x2. And similarly, in the case when z is x1 divided by x2, in which case H inverse of z is now, by swapping the order of x1 x2, is now going to be x2 times z. Or maybe like, I think that should be the same as, let me see here. So, okay, z times x2. So in this case, I will swap order of x1 and x2. So that's why it's zx2 with x1 replaced by zx2. And then now the limit of integration will be with respect to x2. But the main point is that once again, in this case, the h prime of h inverse of z, absolute value, will now be equal to absolute value of x2. And so this is a convolution formula analogously, but in the case of, so there's a typo here. Let's erase this. There should not be any x there. Yep. So this is the formula for the PDF of the product, and this is the formula for the PDF for the quotient. Okay, so that is just a general result. Let's see a quick example. Okay, so suppose I have two random variables, x and y. They're both uniform. And I want to look at their product, x, y. Then I know from the previous slide that the product has the PDF in this form. So just to show you that, this expression here is nothing more than this expression here. Okay, so now we have to be careful once more about the limit of integration. So we know that x times y will be in 0, 1. That's obviously true. But because y is less than or equal to 1, what that implies is that x times y is less than or equal to x. So the value of u here, so this is u is equal to x equal to y. So what that means is that x has to be bigger than or equal to u. So once again, let's recap that. We know the product x times y, but because y is between 0 and 1, so therefore x times y, which if we define to be u, x times y is at most x. So therefore x has to be bigger than or equal to u. So the limit of integration has to start from u up to 1. And because by the independence, f x1, x2 is always equal to 1. So we have 1 here. And then we divide by the absolute value of x. So we have x here. And so this is a simple integration to give you minus log of u. And so that is the PDF for the product. So as you can see, the formula is quite powerful. All you need to know is I just have to worry a bit about the limit of integration. But once you know the limit of integration, that's just a simple exercise of evaluating the integral with a proper limit. And for many problems, that is straightforward. So the next thing is, let's consider, for example, the quotient v equal to x divided by y. And so we say earlier that formula is given here. And I have so many typos, so I apologize. I will try to fix that. There is no x here. It should only be dy. But once again, like a broken record, I just have to worry about the limit of integration. So if v is less than or equal to 1, then obviously vy is less than or equal to y, and y is less than or equal to 1. So everything is in the correct limit of integration. So if v is equal to 1, then the joint PDF is always bigger than 0 for y in 0, 1. So the limit of integrations goes from 0 to 1. And so f v y y is always equal to 1. So that is this limit of integration, which is always equal to 1/2. Now the next problem is that if the absolute value of v is bigger than 1, then in that case, I said that x divided by y is equal to v. So what that meant is that x has to be between 0 and 1. So in that case, I know that Vy has to be less than or equal to 1, which then implies automatically that y has to be less than or equal to 1 divided by v. So that's why my limit of integration goes from 0 to 1 divided by v. And once again, the absolute value of y, and that integral is easily evaluated to be 1 over 2v squared. So the PDF for the quotient looks something like this. The PDF for the quotient looks like 1/2. So this is the PDF. And then it decays down to 0 as v goes to infinity. And so that is the PDF for the quotient. So once again, just to repeat the record, just be careful about the limits of integration. So let us do another maybe curiosity. Suppose I look at, say, x and y, be independent, and I look at the ratio. Then that is the form of the PDF. And because I don't have to worry, because x divided by y, and x is anywhere in the real line, and y is anywhere in the real line, so I don't have to worry about the limit of integration. That is why it's always nice to work with ratio of two unbounded random variables. So I don't have to worry about limit of integration. I can go from minus infinity to infinity. That's the value of y. This is the PDF for x, or that's the PDF for y. And this is the PDF for Vy. So this is Vy, and this is y. And I could complete the square. Turns out to be this. And this is once again a simple exercise. So the limit integration from minus infinity to infinity, but I can replace it from 0 to infinity by multiplying by 2, because the function is symmetric due to the absolute value. So therefore, I have the 2 here that cancels out with this 2 here. So I have 1 over pi. And this is a simple integral, because you can now do very simply. You can just do u is y squared 1 plus v squared divided by 2, in which case the u is nothing more than 2y 1 plus v squared dy. So therefore, I have y dy, so just need to divide by 1 plus v squared. And this is nothing more than the PDF of a Cauchy. So the ratio of two independent, normal, standard normal, turns out to be Cauchy. So you see that all of these random variables, really, they are quite interrelated in many cases. And we know that that follows directly from integral property transform. So now let us take a quick detour. So this distribution turns out to be very important in ST 422. So I think it's a good opportunity to introduce it now, even if you do not care about it now. Having seen it once would maybe make it easier to remember it when you see it the second time. So the main thing is that by seeing something multiple times, we get more familiarity. Okay? So we come to a widely abused distribution in statistics. This is known as student T. And to say a silly story, student T, real name is really William Gosset, who is a statistician employed at Guinness, which, if you're of drinking age, makes really good beer. So if you're at drinking age, and once the semester is over, or even if the semester is not over, you may consider buying yourself a stout, a Guinness stout. But if you're not of drinking age, well, let's just wait for a while. Okay, in any case, suppose I have a standard normal, x, and I let w be chi-squared with m degrees of freedom. And I define this random variable v, which is the standard normal, divided by the square root of the chi-squared. Okay, I want to derive the PDF of V. So how do I do that? I will do it step by step. First, I could consider the PDF of W divided by M. I know for the fact is that if W is gamma and the chi-squared is gamma, then W divided by M is gamma alpha beta divided by M. If I scale, that is why this is not the scale parameter. So I know that it has shape parameter, which is M over 2, that defines the chi-squared. And now because I divide by M, the scale parameter is now 2 divided by M. Because as you remember, chi-squared M is gamma M over 2, 2. So this then, the PDF for Y is simply this form, which is just the PDF for gamma M over 2 and 2 over M from chapter 4. So now the next thing I have to do is I just have to apply the monotone transformation, square root of Y. The reason why I can apply this monotone transformation is because Y is non-negative. So in that case, the square root function is monotone. So by the monotone transformation theorem, the PDF for Z, so this is the part where I apply the inverse, and this is the Jacobian. So this one here I've already told you is up here, and the inverse, this part, is simply 2Z, because as we see, H inverse of Y is, okay, so the inverse function is HY, which is the inverse, is, let me see. Okay, so H inverse is going to be Y square, or is equal to Z square. H prime is going to be equal to 1 over 2 square root of Y. So therefore, we will 1 over 2 times square root of Z squared, which is 1 over 2Z. And so if I divide by it, that will be multiplying by 2Z. Okay. So let us erase this part here, just so we can see more clearly. But that's why the 2Z is simply this part here, as what I showed here. And so some simplification will therefore give you this as the PDF for Z, which is square root of W divided by M. So now I have this part, square root W divided by M. So the only thing left is, therefore, V, which is X divided by Z. I have PDF, which I shown you earlier, before. And the only thing that I have to be worried about is that Z here is obviously square root of W divided by M belongs to 0 to infinity. So the limit of integrations goes from 0 to infinity. So I have here the f of Vz and Z, which is now a bit of a mess, but in the case this is Vz, because f of Vz, Z is basically the product of the PDF for a normal 0, 1, evaluate at Vz, times the normal PDF of this random variable Z, which we see earlier. So this, the PDF of a normal 0, 1 evaluate at Vz, that is E minus Vz squared divided by 2. And the PDF of Z, as we saw earlier, is this part here. You have Z to M minus 1. But then when you multiply it with Z here, that becomes Z to the power of M. And then you have the second part, which is E minus mz squared over 2, which is E minus mz squared over 2 here. And the remaining constant here is simply just this constant here, m over 2, gamma m over 2, 2m over 2 minus 1, m over 2, gamma m over 2, 2m minus 2 minus 1, and the square root 2 pi, which is part of the PDF for the normal. And so once again, remember the gamma integral. That is why we stress, remember the gamma integral. This integral here can be simplified out to be this gamma integral here. And then after some simplification, you get this formula here. And check that m equal to 1, give you the Cauchy PDF. That should be easy, because in that case, gamma of 1, or rather gamma of 1 plus 1 divided by 2 is just 1. And gamma of 1/2 is square root pi. So that gives you the Cauchy PDF. So I want to emphasize that this example here is tedious, yes. But conceptually speaking, once again, there is nothing too difficult. You have to use a lot of concepts you've already seen before and combine them properly, but the approach is very straightforward. First, I say, okay, what is the distribution for W of m? I know what that is, that's gamma. Now, what is the distribution for the square root? I know what that is, monotone transformation. Then what is the distribution for the ratio? I know what that is, this convolution. I saw that before. How do I evaluate this integral? Once again, the gamma integral. Then after that is all algebraic manipulation. So I'm not trying to discount the difficulty of the problem. I'm just trying to say is that, yes, it is a lot of steps, but it is straightforward. These kind of steps are not things that you can do maybe in half an hour. But if, say, your life depends on it, well, I hope that nobody's life depends on deriving the student T distribution. But suppose that, say, your, income depends on it, then that is not such a bad situation to be in. Okay. Finally, if you have as m goes to infinity, the student T converges to the standard normal, and that is really as follows, because as we said, student T is x divided by square root of W divided by m. So if as m goes to infinity, W, which is you can write as chi squared 1 plus chi squared 1 plus chi squared 1, m times the sum of independent chi squared with 1 degree of freedom. So therefore, W divided by m will converge to 1 by Chebyshev inequality, because that's a sample mean definition. So that's by Chebyshev inequality, it will converge to 1. So in that case, you just have x divided by something that converges to 1. That's just x. And so you have uniform. Or just you have standard normal. So the student T is in a sense a generalization of the standard normal. And we will come back to the student T distribution many times in 422, and even one more time later in this lecture slide. So let us move on and talk about the method of moment generating function before we end for today. So we record that two random variables with the same moment generating function has the same distribution. So more specifically, if you have x and y with moment generating function mx and my, and there exists a value b bigger than 0 for which the two functions agree for all t with absolute value less than b, so for all t in the neighborhood of 0, then we claim that x and y have the same distribution. And so this is one of the only magic result in this class, a result we will not prove. So the general application goes as follows. You have a bunch of random variables, x1 to xm. You have a function of them. If you can show that the moment generating function of z coincide with that of some well-known distribution y, then you know that z has to have that distribution. So we see the moment generating function for a sum of binomial, sum of Poisson, sum of normal, sum of gamma, sum of many things on. See also example 6.12, theorem 6.3, and 6.4 in your textbook. So we have seen this technique multiple times. So what we will do is to use a technique to prove one of the most fundamental results in statistics, the central limit theorem. So you may have seen this result before. You will surely see it again in 422. So you will also see the proof of it again in 422. But once again, the aim is to introduce a concept a few times so that by the time that you've seen it, say by the x time, it will become a natural thing. So like I said, one of the most famous limit theorem in statistics, the version we give here is the easiest, emphasis on easiest, but most restrictive. So more general version, much more general. You could relax a bunch of assumptions, such as you could relax the assumption of existence of MGF. The moment generating function does not need to exist. You just need to have, say, the third moment. You also do not need them to be identically distributed. And there are many others. Relaxation. So the result goes as follows. Suppose I have a sequence of random variables. They are all independent. And they all have the same distribution. I suppose that because they all have the same distribution, they will all have the same moment generating function, if it exists. So suppose that moment generating function exists. I now look at the sample mean of the xi. So 1 over n, x1 plus x2 up to xn. So I show that the sample mean minus its expectation divided by the square root of its variance. So the sample mean is x bar. Its expectation is obviously the mean of the true x of each of the xi. And the variance of x bar is simply sigma over square root of n. So variance of x bar is sigma squared over n, where sigma squared is the variance of any of the xi. So that this expression here is nothing more than this. And the claim is that this difference, properly scaled, converges to normal. So this result is true for any distribution. So the central limit theorem is powerful because it says I don't care what distribution you have. If n is big enough, I can approximate the sample mean by a normal random variable. I don't care what distribution you have. The sample mean for big enough n can be approximated by a normal random variable. So the statement of the result is as follows. What the convergence means is really just that for any number AB, A and B, the limit for big enough n of the probability that the sample mean minus the true mean divided by the standard deviation. If you are scaled by square root n, then it lies between A and B, with probability converging to the difference of the CDF of the standard normal, A related B and A. So what that meant is that for n sufficiently large, the probability that the sample mean minus the true mean is at most k standard deviation away from sigma, k standard deviation, probability is normalized, is the difference between phi k, the CDF, minus phi minus k, and that's by the symmetry property of phi, That's 2 phi k minus 1. And some simple calculation will show you that the empirical rule says that 2 phi 1 minus 1 is roughly 0.68. For 2 phi 2, that's 0.95. And 2 phi 3, that's 0.997 and 0.994. So if you compare it against the Chebyshev inequality, which we shown earlier, will give you this bound, then you see that this approximation is much better than this guaranteed bound. So for example, k equal to 1, Chebyshev bound gives you 1 minus 1 over k squared equal to 0. K equal to 2, 1 minus 1 over 2 squared is equal to 0.75. K equal to 3 is equal to 0.91. K equal to 4, no, that's wrong. It's equal to 8 over 9. K equal to 4, that is roughly 15 over 16. So that is roughly 0.93. Right? So 8 over 9. So roughly 0.88 or 0.89, 0.93. And so see that 0.93 is quite further away than say 0.99994. So the central limit theorem gives you a much tighter bound on the difference of x bar minus mu compared to say the Chebyshev inequality. So in a sense, the central limit theorem gives you a much better approximation, but that requires n sufficiently large, while the Chebyshev inequality works for any n. For any n. So then it's just say, is my n big enough? And there's a bunch of heuristic to decide whether n is big enough. But we will not go there. So the proof of the COT is a straightforward use of moment-generating function. So let us go through the proof once. You will see this proof in 422 again. So I let x tilde just be the mean. It just be the random variable minus the mean divided by the standard deviation. And the key point is that the mean of x tilde is equal to 0. And the variance of x tilde should be equal to 1. This should be straightforward to check. So x tilde has mean 0 and variance 1. Furthermore, if I define square root n times x bar minus mu divided by sigma, I can write this as 1 over square root n of the summation of x tilde I by some straightforward manipulation. So for any random variable y, the moment-generating function of the scaled and translation of y is simply obtained as follows. Just because you remember, expected value of e of t a y plus b is just nothing more than e t b, expected value of e t a y. And so you just combine ti as a new constant, so you have at. So as the x tilde I are independent and have the same distribution, by the property of moment-generating function, the moment-generating function for Gn is just the product of the moment-generating function for the x tilde I. Well, because we scale by 1 over root n, we have to divide this by square root n in each of these terms. And so they are the same distribution. I can write this as m x tilde generate. T divided by square root n to the power of n. So m x tilde is a moment-generating function for any of the x tilde I. So to show that this random variable Zn converges to standard normal, I can show that m of Zn t converges to the moment-generating function for standard normal. But the moment-generating function for the standard normal is exponential of t squared divided by 2. That we know. So the show that this converges to this is equivalently to show that the limit of the logarithm converges. And because we know that mZnt is mx tilde t over square root n to the power of n, so that's just n times the logarithm of mx tilde t divided by square root n. We want to show that this converges to t squared over 2. So the main thing is that if I let n go to infinity, then t divided by square root n for any fixed t converges to mx tilde of 0. And that is nothing more than the expected value of e to 0x, just the expected value of 1. So it has to be equal to 1. And so this limit is of the form n times the logarithm of 1. So that is of the form infinity times 0. So this limit is indeterminate. You can't directly evaluate it. But luckily enough, you know from your days of calculus that in the indeterminate case, if you can't find the limit, you can just invoke L'Hopital rule. So the limit of the ratio in the indeterminate case is the limit of the derivative of the ratios of derivative. So we just have to evaluate the derivative. And that is easy. So we have what we have here is this quantity. We want to take the limit. And so we define x to be 1 over square root n, in which case n is 1 divided by x squared. So 1 divided by x squared. And now it's dx. So the derivative, what the derivative of a moment getting function, taking the logarithm, is simply this term. The derivative of 2x is simply 2x. And now you would say, well, can we check whether this has a limit? But the problem is because we know that the expected value of x tilde is equal to 0, which is the same as the moment getting function of mx tilde. Take first derivative, evaluate at 0. So this part here, the limit is 0. This one is 1. This one is 0. So this is again of the case from 0 divided by 0, which is indeterminate again. Okay, so that is indeterminate, but no problem. Let's take the second derivative. So this is the second derivative. The second derivative turns out to be some simple algebraic manipulation given here. And if you take the limit as t goes to 0, you get t squared over 2, which is exactly what we claimed out before here, or rather here. So as you see, the proof is nothing more than write out the moment getting function, show that the limit converges to t squared over 2, and if you try to evaluate that limit, you realize that it's indeterminate. So you just have to say, well, I need to know L'Hopital rule. So if you know L'Hopital rule, then everything follows directly. So there's a bit of magic here. Remember L'Hopital rule and that uniqueness of moment getting function. But in any case, that is the proof of the central limit theorem. So in summary, if you believe the uniqueness of moment getting function, that is nothing more than an exercise in taking derivatives and using L'Hopital rules. So let's end here for today. I will upload the next set of slides in a few days, and I will end our discussion of chapter 6 and thereby all the materials in 14.1. So take care and please send an email if you have any questions. Bye bye.